Good morning, Professor Barrett.
Good morning, Professor Cruz.
How are you?
Very good. How about yourself?
I'm very good. Well, uh,
What's the weather in Mexico City right now?
Mexico is not, today is nice, nice weather. Not too much hot, but I don't know more later.
Oh, that's good.
But
Yeah,
maybe today not raining.
my wife is still in Cholula.
Oh, okay, yeah. Uh, you stay where are you?
I'm in South Carolina.
South Carolina. South Carolina. Yeah. Okay. Okay. Very good. And the weather there, how is
Well, we had some
comfortable?
rain yesterday. There's a hurricane, but that will really only affect the coast of South Carolina, not upstate. I'm in upstate South Carolina. And
Mm.
Wanda says the weather in Pueblo is very nice too. It tends
Yeah.
to be hot here in the summertime.
Too much hot?
Yeah.
Oh,
But your
okay.
altitude saves you from the heat.
Mm. Yeah. Okay. Very good.
I guess Dr. Page is not here yet.
Sorry?
Dr. Page,
Oh, the doctor.
not
Yes,
here.
not yet. I suppose he started the the meeting.
Yes.
Mhm.
And of
but,
course,
but not yet. Not yet in the session. Mhm.
okay, there he comes now, I guess.
Mhm. And then you think to participate in the now Professor Pesh, how are you?
Hi,
Good
good morning.
morning. Good morning.
Yeah, I've been busy with the other material, and of course, I will be going to Mexico about that same time, so maybe I won't participate in the Panama conference.
Mm.
But you're planning on participating, is that correct?
Yes, I am planning to participate because I think that it is an opportunity to present the ideas about interaction.
Yes, yes.
Then I think that it could be a good opportunity. Yeah.
Yeah, I hope that you can present that material on our seminar as well.
Yes. In
Well,
fact,
it'd be nice if Dr. Santilli came to the seminar as well. Then,
yes, it could be, but I don't know. And I think that he don't follow now the um, calendar of the sessions. Then maybe this is because he is not attending, or maybe he's many busy with another subjects. Mhm.
but I guess your student? Let's see, what is the name of the other participant that was going to come today?
Brian Garcia Sarmina.
Yeah,
Yes.
But he not yet uh, connected.
that's it.
No, not yet. Mhm.
Okay, so you're discussing the meeting in Panama?
I am planning to go to the meeting, but it is too much expensive. the, uh, the hotel and the fee for the conference is too high. It's around 900 euros. Euros. Mhm.
Not to
That's
mention
a
the
lot.
plane expenses to get down there.
Yes, it is too much expensive. Then and now I get a discount to the fee, but anyway, I need to pay 600 euros. Euros. Mhm.
Mhm.
Then, but maybe I can go. Mhm.
How are you, Dr. Page? Everything's fine in Canada?
Uh, yeah, yeah, pretty good. Yeah, things are calming down from summer. Not quite so many hot days.
How
But
about those fires? Are those fires put out yet?
no, there are still fires in the north. Uh, it's a long ways from us, so we don't uh, have any direct effects of it. But occasionally we do see some oddly cloudy skies.
Yeah, I know New York City was getting a lot of smoke from the jet stream, I guess, carried it over.
Yes, earlier. Right now, the worst fires are on the western part of the country, so that's quite a ways away from us, about 3,000 miles. So
Well, what happened in Hawaii was something terrible. The fire just tore through the town there, Lahaina,
horrific. Yeah.
Lahaina, I guess pronounced. Fires all over the place.
Yes, it seems to be that type of year where that happens. Um, it's the worst season ever recorded in Canada, at least for this type of thing. There are fires, of course, every year, but on a much smaller scale. Who's to say? Perhaps climate change or just some kind of natural variation. Who knows?
I guess that main city was spared though. The fire never did burn to what was the name of the city there? It stopped. They stopped it from destroying that city. I guess I don't
Yes,
know. I
just barely. Yeah, it was
barely.
within 10 kilometers of the border or the city limits. Yeah, small city of about 20, 30,000 people, but still, it was pretty disruptive for them. They
Well, that's what.
essentially evacuated the entire 20,000 people out of one little area. Not so easy to move to evacuate in communities that far north. So there's
Yeah,
only
they had trouble getting people out of Hawaii. The Maui was the
Mhm.
main city there was destroyed. Really, lots of people lost their lives.
Yeah. So see, Jesus seems to have come and gone. He must be reconnecting. I guess I guess we should probably start our meeting today, even though Brian hasn't shown up. Uh, he may have other commitments. I don't see any emails from him, so.
So, yeah, I've been thinking still about the ideas I talked about last time. In particular, that example of the defining everything was on page 5 of my presentation, where I defined the E1, F1, F2, and F3 in terms of plus and minus signs of the nilpotents, which is and I tried to extend that to 8 dimensions. Of course, Clifford algebras repeat themselves after 8 dimensions, so it seems to almost work the same. It's pretty interesting, but I haven't reached anything definitive at this point.
Mm.
But
So you expect it to repeat in some way.
well, all Clifford algebras have a periodicity of 8. So the interesting thing is I can define the A1 up to A4 only in of for example, E1 is just the sum of all A1 plus A2 plus A3 plus A4, and then F1 is A1 minus A2, A3 minus A4, and so on, just changing the signs without having to give that. The other formula was a formula involving it was much more complicated. But when you go to 8 dimensions, then you have to be a little more careful in defining that. So it gets a little more complicated then. But it seems very interesting that you don't have to use that formula I gave for defining that the nilpotent basis by the much longer formula. You just use plus and minus ones, which is pretty interesting, I think.
But the formula
Like a
that you gave,
spectrum.
so the formula that you gave earlier, would that, I'm not sure I recall it in detail, but that would in principle work all right with 8 dimensions?
Let's see if I think I can get the thing up. I can show it on the screen. Maybe I'm going to.
The point of my question is that I'm wondering how computationally intensive it is. Like, is this something that you can use computer algebra to help you complete?
Well, yeah, that's what I'm doing now. I'm using Mathematica. Can you see the maybe it's not.
Yes, I can see your screen.
For some reason, I can't move it though.
I see your cursor moving.
For some reason, I can't seem to. Why can't I move the? Oh, maybe I can do it like, okay. Let me just show you that one page, maybe where I define those things. Yeah, right here is what I was talking about. So I'm using the C's to represent this, to separate the idea from the nilpotent basis. I use A's and B's for the standard matrix interpretation, but I'm using C's where I'm considering these are the same nilpotents obeying the usual table of multiplication. But you can see we can define E1 as just the sum of all these. Well, that should be adjusted by, if you square E1, it's going to be equal to 6. So you have to adjust that factor by 1 over the square root of 6 to make it a unit vector. And then the same thing here. These will be vectors, I think, with the square root of 2. You have to adjust the factors. Now, the idea is I'd like to go to, I don't think you can do it for all dimensions. You can't do it for 3, but you can do it for 8 is the next one, I think, but I haven't. But just changing the signs, that's a much easier formula than this other formula which we used. Let's see, where's the other formula? Let me go ahead and get that other formula, the general formula here.
Mm-hmm.
Where is it?
So, Jesus, do you have a stable connection? I saw you disappeared and came back.
Oh, okay. Maybe I'm flipping it too quickly.
Yeah.
Let me just find where that one
Yeah.
formula
So
is. That
Justus, are
formula is a
you
little
okay?
more- Oh, right
Yes,
here it is.
I'm okay.
Now, can you see the formula 10 here? On theorem 2?
Yes.
Okay, so that's the standard formula. You see, I'm defining in terms of, you have to put a coefficient in front of each of the nilpotent. But the other one, I'm just using all these coefficients are plus and minus 1, which is, so, of course, there's many possibilities, but this is the first formula I found for defining the what I call the local dual relationships rather than the global duality, which I was trying to define. Okay, so that was a, but anyway, yeah, I'd like to get it at least to 8 to find a suitable basis just by changing the plus and minus signs in front of the nilpotents rather than using that more general formula for any. So it would seem like it has a periodicity of 8, which is, of course, well known for Clifford algebras have periodicity of 8. But maybe Dr. Cruz has things that he'd like to talk about. I don't really have too much to say about this.
No, don't worry. I mean, yes, I prepared something for the presentation, but maybe you can continue, and then after of you, I can present my work.
Okay, well, I've made progress. Like I say, this works for 4 nilpotents. Remember, I'm just distinguishing with the standard nilpotent basis, which defines 2 Grossman algebras. We're only talking about 1 Grossman algebra using the wedge product between C1 wedge C2 wedge C3 wedge C4, whereas the other one, we had the A's form a Grossman algebra and the B's form a dual Grossman algebra. But in this case, we only have 1 Grossman algebra using the outer product, whereas the inner product between any 2 of these C1, C2, C3, C4 is equal to 1/2. So it's a different kind of basis, but it's a base and it's a different geometric algebra. Namely, for example, this is the geometric algebra 1, 3, which is very important in relativity. The Dirac algebra is isomorphic to the geometric algebra 1, 3, or also called space-time algebra. So,
but what's special about these particular combination of signs? I mean, there are 8 possible combinations of signs.
That's right. Well, the way I've chosen for this basis is C1 is always the same, okay? And then C2, C3, and so it's just 3 things taken 2 at a time. So if you keep C1 fixed, the only possibilities are, minus, minus, plus, minus, plus, minus, and plus, minus, minus. But it's not quite that simple when you go to 8.
No, I don't see that, because you have other than C1, if you leave C1 constant, then you have 2 to the 3 possibilities, right?
Well, okay. Well, it's 3 things taken 2 at a time. I have to change 2 signs for each of these things. So 3, I'm leaving C1 the same in all of them. And I'm only varying the sign, taking 2 signs. So that's 3 things taken 2 at a time. Okay, well, you can have minus, minus, plus, minus, plus, minus, and plus, minus. That's the only possibilities for taking 3 things 2 at a time. Now with 8.
But you also have plus, plus, plus.
Oh, yeah, that's true. But that's the special element E1, right? If you square E1, then you get 3. Okay, that's 4 things taken. No, what am I saying? That's 6, right? So if you take remember,
Well, okay.
we get
The
six.
difference being that
Uh-huh.
the E1 represents, the
The one vector
hyperbolic
which has
dimension,
square.
right?
Yeah, remember we're looking at the geometric algebra 1, 3. So we have one
Yeah.
vector which has square, positive square, and the other ones have negative square. I should normalize this by saying E1 is equal to, if you square this thing, you get four things taken two at a time, which is 6. So you normalize E1 by writing, I should divide that by the square root of 6, because then it will have square plus 1. And I should divide this by, if you square this thing, you get 2. So you have to normalize F1 by, to get a unit vector, you have to take 1 over the square root of 2 times F1, 1 over the square root of 2 times F2, 1 over the square root of 2. So these should be unit vectors because we're generating the geometric algebra 1, 3. So that's the way it works for, I should have put that in there. I should have corrected that. I want this to be normalized. So it's 1 over the square root of 6 times C1 plus C2 plus C3 plus C4. But this is then, if you square this thing, you get F1 squared the way it is now is minus 2, because C1 minus C2 squared is minus 1, and C4 minus C3 is minus 1. So you get minus 2. So to normalize it, to make it a unit vector, we have to divide this by the square root of 6, and you have to divide these by the square root of 2, and then it's normalized. And then well, that works out. But if I go to 8 dimensions, I can't find, I can't do a similar thing with, well, I would try even 2, 4, 6, but there doesn't seem to be any way of doing that with just using plus and minus signs for the coefficient.
Well, it sure isn't this like just related to the what's the right word? I mean, the fact that you have 2 minuses means that this is going to be part of the set of 3 basis vectors. But if you have 1 comma 7, say, then you need a way of generating 7 combinations. But in some cases, you would have, say, 4 possible minus signs. You could have, you'd have.
That's right. With
the number
8,
of ways of choosing 2, the number of ways of choosing 4, right?
Yeah, that's right.
You don't want just 1 sign or 3 signs or 5 signs. You want. But if you have 7, there are a lot more signs involved. Right?
Oh, that's right. And it gets more complicated, and so it's a combinatorial thing. But okay, that's why I've gone to Mathematica now. The only way to do it was, but that's right. So for 8, well, for example, for 2 dimensions, you have G11, and that works just fine. So anyway, these are the types of problems I'm thinking about now. And I'm trying to also we know that any Clifford algebra has a periodicity of 8. So all I really have to do is figure it out for 8. And then, of course, you can take subalgebras then to get the smaller ones in between. Anyway, that's the type of thing I'm thinking about now, which is, I believe, is interesting. But again, it's more, there are many more possibilities when you go to 8. But there I'm looking at 4 minus signs. But if I take the same thing, so if I take E1 equal to the sum C1 plus C2 plus C3 up to C8, then I have to normalize that by, well, 8 things taken 2 at a time is 28. So I have to normalize. If I take the sum of C1 up to C8, I have to divide by the square root of 28, which is 2 times the square root of 7, which is fine. But here I have to know, it's a little more complicated to get these things normalized. And well, there's a little more calculations to be. Remember, I want the inner product E1 dot F1 equal to 0, E1 dot F2 equal to 0. All the inner products of the standard basis, E1, F1, F2, have to be equal to 0. So it makes it a little, and then if you have 8 vectors, well, again, the same thing, E1, then you have F1, F2, F3, F4, F5, X, F6, and F7 would be the standard basis. So, you know, it becomes a combinatorial problem that I'm looking at. But anyway, I think it's interesting because, well, that's a different, well, there are, of course, many ways of representing this basis. And of course, well, anyway, that's what I'm looking at, but I haven't come to any definite, it looks like it'll work out, but I haven't, well, it's interesting. I've looked at several bases and now I'm looking at it with the help of Mathematica, which is very powerful to calculating these things for determinants. But the thing is there a way of calculating the outer product with for say n vectors? How do you calculate the outer product of vectors with Mathematica? I'm not quite sure how to. Anyway, my knowledge of Mathematica is limited, but I imagine there's general programs for calculating the outer product of, say, n vectors.
Well, if you represented them as matrices, like 1 by n matrices and n by 1 matrices, then
yeah, you calculate
the outer product is pretty straightforward.
That's right. But if you take a non-standard basis, just an arbitrary basis, how do you calculate the product there? Well, let's see, would that be just the determinant as well? Then it's the determinant times the, for any basis, you can calculate the outer product of by just taking the determinant. Yeah, I guess that's true.
Yeah, the determinant is defined independent of the basis. So
yeah, that's right.
I think that's true.
Well, of course, then that's where the metric becomes important, though. With a different metric, for example, with the metric 1n, well, yeah. So, yeah, you have to normalize those vectors first. Well, it's a little more complicated. Well, no, you can calculate the outer product. That's fine. But then the yeah. Now, yeah. If you take the square of, say, the bases, then you have to take in consideration the signature of the metric, which is 1n in this case. Well, that's a Lorentz metric. That changes the problem a little bit. Well, anyway, so I've got to think about these ideas a little more before talking about them, I guess. But I think it's interesting.
Okay.
Just
perhaps
perhaps
in 3 weeks. Perhaps in 3 weeks' time, you'll have
yeah, I can say more. Make more sense.
Give us in a little more detail.
Yeah.
Okay.
So I'm willing to. I'll stop my sharing and let Hayes talk about what he's prepared, which I haven't really prepared anything other than.
Thanks a lot. I'm going to share now my screen, and this explains the idea that I am working. Okay, I switch to this because the invitation of Professor Santilli to participate in the Congress in Panama, then I take time for preparing not only an abstract that is that I need to send, but to work in the writing up paper or a draft of a paper for this subject. Then I am not today to speak about graph theory and Clifford algebra, but the ideas that I have been working in that direction are taken again here. I have not too much. Maybe you can see. Sorry, I am going to put more. Okay, it's I think it is in good size for you, or do you need more?
Yes, no, that's fine.
Okay.
Yeah.
Here is the principal idea of this, and then I am going to use the category theory approach for defining the class of objects that is the class of bodies in state equilibrium. And then I am going to define interaction like a set of morphisms between objects in the category. How you can see in the next parts, some of this idea needs to be modified because I found a better way of defining the category, and in this way defining some relations between different kind of categories that are representing the interaction process. But here is the principal ideas that I have been used in the past. Okay, then I'm going to the next page. I'm going to. Sorry.
There's one typo perhaps there in your introduction, if you haven't noticed.
Yes.
So the F algebra.
Okay. Here.
Say F algebra.
A G. Or
ALGEBRA.
No, I don't catch your comment. Sorry.
Just the typo.
The type.
Typo. The spelling mistake.
from the two lines from the bottom of your reference, from the bottom, algebra.
Oh, okay, yeah, okay. Then I need to
That's okay. Okay.
Just to let you know that just later you probably would catch it, but
yes, is in equilibrium state.
Right, two lines from the bottom.
Oh, here, okay.
algebra. Yeah.
Okay, thanks. I
Okay.
I need to correct that. Okay, but now I will go ahead in the introduction because it is only in progress, and now I go directly to the formal definition of interaction. Then this is the central part of the presentation today, because here I repeat only that I am using the category theory approach, but here we start defining an F algebra formally like a triplet R, F, and phi, where F is a commutative ring, R is a ring, and phi is a homomorphism in the going from the F commutative ring to the center of the ring R. And this definition is used for define because are the principal properties of an algebra. Then I am starting with this definition of algebra, and then we can say that this algebra is representing the states of a body. Because this algebra properties, we have this property in using one element of the commutative ring, I am going to use in the from here the name field. Then alpha is an element of the field F, and A and B an element of the ring. But here we have an operation between an element of the field and elements of the ring, and it is very important because here we are defining, in fact, that the product between elements of the ring is the tensor product, because this property that we are defining here. Then this is
example would be the ring could be a Clifford algebra, for example, and
for example, a Clifford algebra, of algebra. Sorry.
F could be a field and R could be a Clifford algebra. An example of that structure.
Yes.
What does a CEN stand for?
CEN is the center of the ring. That are the okay. Of the ring.
Okay.
Then and here I have the definition of objects based in the prior definition, in the prior formal definition. The class of objects are elements of this category and are represented here by bar phi. we call it the class of equilibrium states. Here is an important difference with the um, um, ideas that I used before, because it is better to associate a body with a category, and then the equilibrium states of that body are the objects of that category. Then, in this way, a body is an algebra, and then this algebra are defining the properties of the states of the body. Is defining how the states can change in the body, and how those states can be modified by an external body. Okay, here there is a discussion about the properties, about the meaning of equilibrium. It is important for me to say, to emphasize that the equilibrium state is not referred here to the concept of equilibrium in a body in movement, but only to the state of the system or the state of the body. And then we can use the identification of one algebra with a body. Every body is related with one F algebra. Okay, here are only the illustration of this idea. This is the body in equilibrium state, and how the equilibrium state is altered by there is some process morphines in the category that take to the body again to an equilibrium state. And now it is we have here an important thing, because if we consider the two bodies, then we are speaking about two algebras, and then we define a ring of homomorphisms between these two algebras. This homomorphisms have this property, and this in fact is defined now to the intensity action like a functor between these two categories. Then we have here a category phi 1 and phi 0, not, and then we have a functor relating these two categories. Then for And this means that for the idea of interaction, we are speaking of a functor category. In the next part of this work, and I am presenting some of this idea, but I need to modify the part of the text because I need to adjust this concept that I have defined here. Because, for example, in this picture that we are speaking about the concept of interaction between two bodies, here IOR is an amorphism in the category 5O, but IO1 is an element of the functor category. Then they are not in the same in the same level, and then we need to what's the word? We need to take I not to one level up in the way that we can define this composition that's here. Because here composition requires that we are speaking about the same concepts. Then I need to modify this because I need to what is the word that you are using commonly for make an upgrade of the in the category of this kind of objects. Then,
It's a graded algebra then or something.
excuse me? Because here I am going in terms of an super algebra between these two algebras. And then it is an important thing because I am going from one algebra of degree 1, we can say, and then we take these two algebras of degree 1 and get an algebra of degree 2. And this is very important because this is like the product of two vectors that is giving to us a b vector. Then is this gives to us an object outside of the category.
Very interesting.
Then this is the general ideas that I need to correct in this text because there are mixed of concepts here that I need to reorganize. here in the next figure, we have an opposite category. Then we have here two categories, and we have here a functor and another functor, but here we have a covariant functor, and here we are going to have a contravariant functor. Then in these two pictures, we can see that the duality concept are now present in this formalism. And then when we have here how the interaction of the external body change the state of this system, then we are speaking about one functor that is going from the object or from the state in this category from excuse me, to the state in this category, and then produce a process that changes the state in the category phi naught. Then these functors then are of the type of how is the name of sorry, it's defined in a comma category that is one. I don't know if I can write here. I am going to try to annotate here a figure. Then here we have one object in the category 1, and here we have an object in the category 2, and then finally we have in the category 2 a different object, and then we have a morphism here that is I-O. And here is how the external body interacting with the object 2 are real. Okay. I'm going to say that this morphism, that this functor is F and this are G. is RG. And then we have here an internal process in the body too, that is IO, that is one morphism in the coma category. Then this idea is too much useful for describing the process of equilibrium in the affected body by the external body. And then when we speak about this this other process, then we have here a similar thing, but in a different way, because we go from one equilibrium process to another equilibrium, from one equilibrium state to another equilibrium state inside the body too. Then here this IO is different because it's amorphous in the body too. And then this change produce an interaction in the body one. Then I only need to put this, and this is the action of O in one. Oh, sorry, I am changing the notation. Is one of. Then we can see here that IO1 is the dual of I10. I'm going to take this notation. Then this is the idea that I am presenting here with these two kinds of figures that I am using, and are I think that is important because this relation between algebras are taking to giving to us these two dual process that we can find in the algebra. Then this is the the ideas. And I think that this is the principal idea, and that I want to present here. I'm going to. Oh, okay. Then, and this is the principal idea that. Now the figure is fixed in my screen, and for you is the same.
Yes.
Yes.
Sorry, I need to erase because now is okay. Then,
Professor Jesus,
yes,
I have one question with
yes,
the interpretation from the last figure. I think it's below 2.4, equation 2.4, the figure that it's in front. Why can you not think about the interaction as an adjoint functor? Because you have the first interaction that is coming from phi 1 to phi 0 in the previous diagram. And then you have like the response of the interaction between phi 0 to phi 1. But recently I have been studying some subjects from category theory, and I came across with the term of adjoint functors that I think it could be maybe another way to represent like this interaction I 1 0, just as a comment.
yes. That's the idea of duality between these two kind of functors, and one functor covariant and the other contravariant, is behind the idea, or excuse me, the concepts of adjoint functors. Then at the end, I am using that concept, but here we are starting with the principal definitions of this kind of functors.
Okay, Professor. Thank you.
I am to. Okay, now, then here I insist that in this draft that I am using, I am not put all the required formality for the concepts, because I have not enough time. I am using an old version of these figures, and then the concepts are too much mixed. Too much mixed. Sorry. Then here we need the idea is that after of looking about the properties of the system, then we can start working in the idea of the properties of the process of mediation. Then here, when we speak about intensive and extensive properties, we are using different interaction. We are processing different kinds of interactions of the same kind. Then in this concept, I understand the same kind of process, considering that the action of phi 1 on phi naught is of the same type of phi 2. Then I O in blue is possible to composite with IO in red. Because if this is not possible, then I need to use here the tensor product, because these interactions are of different kind. Then when we speak about the intensive properties, we are thinking that the action of these two bodies are expressed in this property. Then we can speak here about extensive properties, and then this is equivalent and non-resultant in action of these two bodies in the body phi naught. Okay, then this is an important idea, because it is now saying to us how the action of these bodies can be expressed like only one action. And then we speak about extensive properties. Then here we have now this definition of intensive property. Intensive property is related with the size of the action of this object phi j. Here I need to put how these actions permit to us to define an preorder category. And this preorder category can say to us that the intensity of the actions are changing, and then we have in this case defined an intensive property of the system. This is too much important, because we have two kinds of property here. One property are extensive, and the other kind of property are intensive properties. Then you can see that this action of the extensive property is experienced by, sorry? No, is experienced by the body phi not like a composition of those of the interaction of the separated bodies, but in the intensive property, we have that the action of body phi j are in one preorder category, and then we can define it this way: how is the size of the intensity? And with these two ingredients, we can define some property that are used for the measurement process for the observer. Then the observer can use different kind of properties in this kind of taking dates from these kinds of properties. Then one observer is a set of processes that are related with that kind of properties that are defining the state of the system. Then this is the first ideas that can take to us to the definition of one observer. First, the idea that we have a set of observables that are used for describe the system. And after the problem is how we can speak about observer. Then I here we are I want to consider the two different kinds of bodies and put in the category of observer, H of 1. Here is the pictures that I was looking for. Here we are speaking about two kinds of observers. Now the observers are represented by psi, and side 1 and side 2 are the observers, and they are interchanging information between. This information in the prior picture is interchanged with light. Then we, in this moment, we select light that like the interchange process between the two observers, and then the two observers are observing the interaction between two different objects, and then this information that receive each observer are interpreted and then are one process of interchange between the two observers. And this is the principal ideas that I am here including in this draft. And then here there are another ideas, but I need to review all of them first. Then this is the material that I had prepared for this presentation. Mhm.
Yeah, so I suppose there's many kinds of possibilities for these various algebras and interactions between them, representing each body can be acted on by a different algebra or whatever one has in mind, I suppose.
Yes, but I think that this kind of algebras have some characteristics that are defined in the first part of the paper, because I defined the a body like an algebra, and then a functor between two algebras, a relation between two algebras are functors that have implicit the idea of duality and the idea of tensor product. Then I think that with this, we can speak that we are going to use a multigrade algebra. And we are going to use two kinds of algebras. One dual of the other.
I suppose each of these algebras could be represented by, in terms of the tensor algebra. Yeah, the tensor algebra plays an underlying role in all these algebras, does it not? Or
yes, this is the idea. Then the tensor algebra permit to us to define this kind of formalization. In fact, the idea of interaction in the category theory approach is organized, taking in means the idea of observers and interactions that I was working with Professor Osiewicz in the problem of electromagnetic interaction. Then there we have the definition of observer is based in a tensor product of two of a vector and a covector. And then the idea is used to with this formalization, we can find this kind of definition of observer in a better formal view.
That's interesting to me because I, yeah, a vector and a covector is one possibility for the definition of duality, but I have this new definition which arises from these geometric algebras or Lorentz signatures, which I call Hermitian or not quantum duality, which is it certainly must be related to all these ideas as well, since they're all part of the tensor algebra. But I think it is a different concept of duality that it'd be interesting whether you could extend using this instead of a covector and vector, this local concept of duality, which I was talking about in my talk, and which I'll probably talk about next time in 3 weeks, I guess.
Jesus,
Yeah.
in one of the graphs, you showed this thing called a recurring process. I think the next graph, next picture.
And then this is the next here.
Yes. Yeah. So this is something like the definition of a clock. Is that correct?
Yes, this is the idea. Is the definition of a clock. Mhm.
Of what?
Sorry?
Clock.
Definition of what?
A clock.
Clock.
A device for measuring time.
Yes.
Oh, a clock. Okay, I'm sorry.
Yes, a clock.
A clock.
But this I've been interested for a long time in Oshevich's Zbigniew Oshevich's definition of material body as a process involving a clock. Right? So in addition to having a velocity, which is sort of something inherent in being a process, right? Then we also, in addition to the velocity, we also need the clock of the body, right? And this connects to the idea of duality because, so the process is represented by a vector, but the clock is represented by a covector. Right? So to represent a material body, we need both a vector and a covector. And I'm not sure how that kind of duality could possibly be represented in the duality that Dr. Sobczak is talking about in Clifford algebra. It still doesn't occur to me like how this could be, so that maybe it's like if you think about how time enters in relativity and you end up with a hyperbolic geometry, right? Then the duality between vector and covector is like the duality between the hyperbolic part of the basis and the Cartesian part of the basis.
I think these are interesting ideas, but like I say, this idea of a vector and a covector is like what they call the mother geometric algebra. That's a geometric algebra of neutral signature n comma n. But this other type of duality I'm trying to discuss arises with Lorentz signatures, either 1 comma n or n comma 1, or complex algebras, which really encompasses all geometric algebras, just as the duality, covectors, and dual vectors and covectors also encompasses all of matrix algebra as well. So, but I think there are two distinct ways of looking at it. That's what I'm trying to get at least.
Here, I am trying to start from the definition of interactions, and then a clock is an interaction. Because a recurring process is altering the state of the psi object that is of the observer, and the when he got to the equilibrium again, then he say that time is going, and then he received again an interaction with the object phi o, and then is going out of equilibrium, and that. Then you can see that when we see, when we read the process in the body side of, then we speak about one measures that needs 2 points, and then we have here a covector. But when we receive the lecture and go to the order pre-order category, we are speaking about vector. And then this process are defined by the way of the how the interaction process is going. This is the idea that I am trying to use here. Then all the concepts like properties of matter, interaction field, time, space are only here reflecting different kinds of interaction. This is the general idea in the formalization here.
Professor, I have a question, more
Yes.
like a curious question, not maybe for a future idea to develop. Is that, have you ever thought on developing an interpretation of a natural transformation between the functors of interaction?
Yes, maybe, but this is the wave of going in the exploration of the properties of this kind of relation between two interacting bodies. That is, for example, I can speak here in the phi O in a system that is going in a recurring process. Then here we have a system that is how you say it, that is starting an action to this this body. This is a functor, but the change of states is taking a different kind of functor here, and then we have here two states in the body psi O. Then we can say that this process is a natural process here, and that is the terms natural is related with the natural transformation that is related the two functors that arrived, excuse me, the two functors that related the different states here with different states here. This is the idea. If I understand in the correct way your question, then natural transform is used necessarily in the formalization.
It's like it's implicit on the definition.
Not implicit in the definition, but when the idea is when I decided that a body is an algebra, and then we are going between two algebras, then we are looking about the properties of those algebra and how one action in phi O, that is how a functor from phi O to psi O can change the properties here. Then I am producing a change in the algebra here. I am producing process here, and the production of the process here is by the kind of results that we have is a natural transformation. Then I think that this is not in this definition, but it is necessary in the way of we can describe in a correct way how how one object is transformed or related with another object in this category. Mm-hmm.
Okay.
Mm-hmm. Okay, and thanks a lot by the comments. I need too much work in this draft, but I wanted to advance in the organization of this, have the first step.
Yes, I think it was it was good. I mean, it's reviewing some of the things that you presented previously in the seminar. And maybe it also serves to illustrate some of the things that you have, some of the methods that in category theory that you have not yet actually presented in the seminar as in terms of the methods. I know in your previous presentation, you were just beginning to introduce some of the necessary ideas in category theory, but you did not get quite to the point of defining F algebra, for example, in category theory. And I think it's interesting to know from the sort of mathematical approach, like separate from the physics, the application of the mathematics. But it's important to know the sort of foundational mathematics as well. So I guess it's specifically the treatment of F algebra that you give or you imply at the beginning in your abstract. It seems a little bit unconventional, or maybe I should say more abstract than the usual definition of F algebra. That's when it's applied to physics. So it might be good to have. I'm not sure whether in this paper or in future presentation, perhaps you can give to us at the seminar about these mathematical technique.
Yes, I can. I wanted to take this presentation in the same way that I use it in the first part here. In the first part here, because I think that with this kind of formalization, then we can arrive to a better understanding of the interaction process and maybe to apply to some problems. The idea is to in all the document that we can work in the same way.
In your abstract, can you show the abstract again?
Yes. Okay, here it is.
Is that where I saw it? No, perhaps it's in the introduction.
Just after the introduction, several problems, and here is
yes, here. Yes.
Yes, here is. It is.
This notion of this triple, right? Of this.
Yes.
And so not the physical interpretation, but the mathematical structure that you define in terms of phi, like the role of this function phi that maps.
Okay. Mm-hmm.
It maps elements of the commutative ring, right? So scalars or something like that. So it maps scalars into a subset of vectors, I guess one could say, or at least elements of the algebra. And it isn't immediately clear to me how this injective property gives rise to
Yes.
F algebra, right? Maybe.
Yes, this is the idea, and this is the formal definition of algebra starting from in category theory. Then I am going to put more detail here in the way that it is more but here the idea is that when we start from the commutative ring F, then we apply some kind of injection in the ring R. And the way of going from here to the ring R is through the morphism phi here. And it is necessary that this homomorphism be injective in the way that all of elements of the field F can be inside an element of the ring R. This is the idea, but I am going to put more detail in here, speaking about different kinds of relation between categories. That is the base of this kind of definition.
So, for example, in Clifford algebra, this injective property is fairly obvious, right? It's to take scalars and map them into elements of the Clifford algebra that behave like scalars, right? So
the center of Clifford algebra is generally the real numbers and the pseudoscalar element together. Sometimes, of course, the center is just the real numbers themselves too, of course. But yeah, maybe could be a subalgebra that you're considering as a in terms of R, your general ring, rather than just the center of the ring, which is just the commutative element.
For example, here we can speak about the. I think that if we think by a moment in a three-dimensional space, and then we have two covectors defining a plane and a vector defining orthogonal orthogonal address. Then we can here think about the problem of going to the covectors, to the covector product, and to localize an element of that in that space. Then we need to use a morphism for going from the scalar field to the localization of that, because I can define in that plane two kinds of scalar fields that describe the localization of the required point, for example. And then in this way, I am using two different fields, and then I take the value of one field and get one ISO value of the other field, and then taking the value of the other field, I get the required point. Then when this is made, we are going to the condition when the this plane of or surface in 3 dimensions is wielded from taking the kernel of one orthogonal, no orthogonal, of one independent field. I don't know if I explained it in correct way, but this is the idea.
I think it would be good to have a discussion or a presentation on just this point.
Okay.
In the future.
I think that it could be very interesting and productive discussion. Yes. Mm.
Okay.
Then I can prepare for the next session of the seminar, the ideas behind this. Mm.
Okay, I think that would be very useful, especially to me. Dr. Sotrick, did you have in mind any subject? Like you did have the thought that you may be able to present something on the higher dimensional constructions.
Yeah, I'll be able to talk about that. Also, I'll talk about this other concept of what I think is another concept of duality. Brian was interested in maybe Brian had something to say about that he wanted to say today.
About the strong complementarity, I thought maybe it was related to the definition of
quantum computers, the language of quantum computers was which my ideas are basically heading toward, to understand how to apply it as a language for quantum computers. But,
yeah.
But basically, this other idea of duality that I'd like to talk about more, what I call local duality. You don't have to use the term quantum or anything, just local. Global duality is the standard definition of vectors, covectors, but this local definition is what defines these Lorentz geometric algebras of signature 1n or n comma 1, which seems to offer a different concept of duality, really, than the standard covector vector concept of duality, which is, I think, interesting.
Yes. I don't know if we have time. Maybe I can present something really quick, just to get some ideas about the way I'm working this part of quantum computing interpretation, and or maybe the next session, I don't know, or maybe in 2 sessions, if Professor Jesus and Professor Garrett want to present their work.
Well, maybe you could spend some time on your ideas as well. I think would be nice. So maybe you could
Okay.
divide.
Yeah.
among-
Yeah, well, okay, then let's tentatively say that in 3 weeks' time, we might have, say, as many as 3 different presentations, small summary presentations, and sort of on these separate subjects, rather than a large subject, then just focus on one smaller area and discuss that.
Mhm.
Okay.
Okay.
All right.
Then we can organize for a presentation about 20 minutes approx. or
Yes.
something like this.
Yes.
Okay.
Yes. I think that would be very, very good.
Okay.
All right.
Okay.
Well, let's try that in 3 weeks.
Okay.
Okay. Sounds good.
All right.
All right. Nice seeing you all.
See you.
Have a good end of summer, and at least in Canada here, it's going to be a little bit cooler in 3 weeks, so I won't have to worry too
Not all
much about
wiped
the
out
weather.
by floods or fires, which seem to be the main thing.
Yeah, yeah,
Well,
fires or hurricanes or you name it. This year we
or
seem to have
nuclear
everything.
bombs, for example.
Okay, bye for now.
Yes. Take care. Take care, professors.